called myoglobin. It's not stored in anything, it's just dissolved up inside the fluid contents of the cell. And it's red, and that's why muscle looks red. And myoglobin binds so your muscle cells, even though they're really well supplied with blood, don't rely on the blood supply alone to deliver oxygen. They hoard oxygen by being filled with myoglobin, which binds and holds on to a great deal of oxygen. It's actually a pigment molecule, and very much like the stuff inside blood, red blood cells. So when you take a piece of meat and you wash it really well so it doesn't have any blood on it, okay? If you chop that meat up, don't you get some juices out of it? That's not blood. That's the myoglobin from the inside of the cells being released. So here's a tidbit for you. Muscle cells that have to do a lot of work will be really, really red, dark meat, okay? They'll have a lot of myoglobin. They'll store up a lot of oxygen in order to survive times where oxygen loads are very low. Whereas white meat, looking at a chicken, the thighs versus the breast, the white meat doesn't store a lot of myoglobin and can't go very long when oxygen supplies are low. We'll apply a lot of this probably by the end of the week in learning exercise physiology, strength versus endurance muscle, red versus white muscle or pale muscle. Okay, so one muscle cell most of the muscle cell is packed full of contractile myofibrils. One muscle cell is a myofiber. It's filled with bundles and bundles, contractile bundles called myofibrils. And here they are here, big red bundles of contracting threads. About 80% of the volume of the cell. Now let's look at an individual myofibril bundle. One, so one bundle, one myofibril bundle in it, inside it has many tiny threads of myofilaments, and they are of two types. So if we look at a bundle, lengthwise, and they're all stacked lengthwise in the cell, if you look at the bundle, it's going to have running lengthwise two types of myofilaments. And those myofilaments can either be actin or myosin. Okay, now I'm going to work backwards. Actin and myosin myofilaments are bundled together in a single myofibril. The myofibrils are bundled together in a single muscle cell or myofiber. People are like, I look at that face, the face I see right now, yeah.
Okay, so that whole thing is a muscle cell.
One muscle cell, myofiber.
Got it.
Filled with myofibrils. Let's do it in a hierarchical order. Myofiber equals the cell, and it's got
Fibril bundle.
fibril, Fibril, And then each myofibril is myofilaments
Got it.
of actin and myosin. Myofiber filled with myofibril bundles. Let's put myofibril bundle here to help you. Filled with myofibril filaments of actin and myosin. Now those actin and myosin filaments are arranged in a very specific way that allows that whole bundle to shorten. Okay? So when a nerve signal runs down a muscle cell and the whole muscle cell contracts or shortens, it's because each bundle with its individual actin and myosin filaments, each bundle shortens. And when they all shorten, the entire muscle cell as a whole is able to shorten. So the next step is to look at one of these bundles, okay, one of these myofibril bundles, and look at the arrangement of myofilaments of actin and myosin within it. It's the arrangement of actin and myosin filaments that allows the bundle to shorten, and therefore all the bundles to shorten and the muscle cell to contract. All right, so here we are in another picture. Now this is what it's going to look like under the microscope. Skeletal muscle looks banded or striated because the actin and myosin filaments in the bundle are thick and thin, and they create kind of a diffraction pattern. Light waves bounce off it, and it looks very grid-like. So here we have our individual muscle cell, our myofiber, and here are the individual bundles, the myofibrils, and we're pulling out one myofibril to look at the arrangement of actin and myosin, red and blue, myofilaments in that bundle. So remember that this bundle runs the whole length of the muscle cell. Now what we're going to do is take a look at this bundle, and it has a nice obvious pattern to it. It's kind of stripy. Stripes. Kind of see red, 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 a little bit lighter on the sides. These little stripe zones are called a sarcomere. And it's more than a look, it's actually a little mini zone of contraction. So, one right here, and one right here, and that's this one right here. So the center of each zone, it's the center of each zone are thick myosin filaments right in here. It's mostly myosin filaments. And you can see down here, they're really thick, and that's why the center of the sarcomere looks really, really red and dark. On either side of it are the thin actin filaments. So you've got actin here and here.
Oh.
Now if you look, and so heavy myosin in the middle, the center of each sarcomere looks really, really red. Paler on either side because it's mostly these thin actin filaments. So each sarcomere has a banded appearance of being dark in the middle and then light on either side. So we have dark in the middle and light on either side. That's one sarcomere.
That makes one.
Now, let's look at these little guys in a little closer detail. So we're looking at this zone right here. The actin filaments are thick and bristly. They're covered with little bristly heads that have the ability to move back and forth and to attach and unattach to the actin filaments.